Hello YouTube world and welcome to my channel. This will be my first English video, so I would like to apologize in advance for my English. I am not a native English speaker, so there will be some annoying accents, some bad pronunciation, even some stuttering. I'm trying to do better, but as you all know, practice makes perfect, so maybe in time it will get better. Now, enough about me rambling. Do you remember this power supply? Well, you should. This is the very same power supply from Tony359's video. You know, the one that had his flyback controller blown, a thin track melted away, some problems with the gate driver for the PFC section, also the Zener from that driver, and so on and so forth. Tony managed to make it work again, except the PFC section, which doesn't seem to want to work. The voltage on these caps should be 380, maybe 390 volts, but it's not. So what is the issue? Well, this is why the supply was sent to me. As you know, I tried to help him fix it, but it didn't work. So Tony proposed he sent the supply to me, and I tried to fix it myself, at least the PFC section. In fact, he sent two of these units, but in this video, I'll take a look at this one. First of all, let's take a quick look at it. Mains come in here. We have mains filtering, two common mode chokes, 4 X2 capacitors, a bit oversized filtering if you ask me, but hey. Y2 caps all over the board. Then, what else? Flyback auxiliary supply, pretty standard, although I don't like this. The flyback transformer is way too far from the controller. And it has these thin tracks, also some wires, as you know. But hey, this is how they did it. PFC section with two MOSFETs in parallel. Some more filtering here. NTC. The relay strapped by an NTC, of course. PFC inductor. Current shunt. Pretty standard, except this one. This is after the rectifier, the bridge rectifier. Not sure what it's doing here. These are the connectors for the modules. Since Tony did his best, but the PFC didn't cooperate, I felt I needed to dive deeper into it. So I went ahead and did a reverse engineering of the mains input and filtering and the PFC section, just to make sure I don't miss anything. Sorry, I did not do that on camera because it takes a lot of time, lots of hours of work, especially since this is a multi-layer board. By the way, I hate multi-layer boards, but I did another video with the reverse engineering process and I will link it in. Most of the through-hole components do not have values because I would have had to desolder them to get the proper value, and I did not want to do that unless I really needed to, because it is a multi-layer board after all. Also, the same with the SMD caps. They would have had to be desoldered to get their value. Too much unnecessary work. What I wanted was the connections and the configuration itself. Values are beside the point. So, this is the main input and filtering. Two common mode chokes, lots of X2 and Y2 caps, then comes the bridge rectifier. And after it, there is another common mode choke, which I'm not sure what is doing there. This one. Why would you need it? More X2 caps, then the relay and the NTC, which straps it at startup to limit the inrush current caused by the main filter caps. These ones. D4 shunts the PFC at startup, then it is turned off by reverse bias once the PFC starts up. Then the PFC itself. The active power correction circuit is basically a boost converter with its inductor, diode and MOSFET in the well-known configuration. Only in an active PFC it performs a few specific tasks. Besides boosting the rectified mains voltage from 340 volts to about 380 or 400 volts. That means the power supply becomes immune to line level changes, and also that it can work with universal mains. But the most important function is the power factor correction itself. The PFC changes the way that the power supply draws its power from the mains. As we know, without PFC, mains current waveform on a switching power supply, in fact the same as with the 50 Hz power transformer followed by the rectifier and filter caps, is very sharp and narrow. That means lots of harmonics, but even worse, you get that peak flattening due to the fact that the current is drawn from the mains only at the peaks. The PFC solves that by making sure the power supply draws proportional current from the entire waveform, thus better harmonics and no peak flattening. Also, PFC corrects the phase angle between mains voltage and current waveforms, thus you get a power factor usually at least 0.9. This is the 12 volts auxiliary supply. It powers the PFC controller IC, MOSFET gate driver and the relay coil plus the 393 comparator. And maybe some other parts of the board which I did not investigate because they are beside the point here. The relay itself is powered with some delay at startup, and a half-wave rectified mains is used to slowly charge a capacitor through two resistors. And when the voltage on that capacitor reaches a certain threshold, the MOSFET is activated and it powers up the relay coil. The Zener diode is there for obvious reasons. It regulates the voltage for the gate. It limits the maximum voltage that the capacitor can charge to. The comparator sets up the under voltage local threshold for the PFC controller, meaning it makes sure that the PFC cannot work unless mains is at some specific minimum level, and it does that by controlling pin number 15 of the PFC controller IC. Although that pin already has an under voltage lockout system included in it, but hey, they felt they needed to do it with a comparator. Maybe this way they get a more precise threshold. I must say I do not like the fact that the relay is placed after the bridge rectifier. It is switching a DC current this way, and you never want to switch DC currents with a relay unless you really have to, especially with such a high voltage here. Remember, 340 volts here. But maybe they had to do it this way due to PCB space available and maybe some guidelines. I don't know. But as I said, I do not like it. Then the PFC controller itself. It is quite complex and not so easy to read, I know. But I haven't had the time to design a specific Eagle Fire for this controller IC, so I had to make do with a generic deep 20 symbol. The PFC controller seems quite complex for what it needs to do. Lots of parts, lots of traces, lots of pins. And also the controller itself already has a 1 amp gate drive totem pole output at pin 20. So it wouldn't have needed this gate driver, although this driver supports 3 amps. So maybe that's why they used it. And speaking about the gate driver, do you remember how Tony pointed out that pin 8 should have been connected to pin 1? Indeed it should, or at least that is what the datasheets say. But I did check, and it seems that it is already connected internally. I measured them almost a dead short between pins 1 and 8, about 300 milliohms. So maybe that is why they did not trace pin 8 to pin 1 on the board. They would have had the space to do it since it is a multi-layer board. Anyway, enough me talking theory, let's get back to work. As you remember, this controller exploded. Why did it do that? Well, I'm not sure. Flyback supplies are very reliable, and I don't think it is this controllers itself. Meaning, I don't think this is a weak controller. What I do think it is that it is a problem with the layout. As I said, the transformer is way too far from the controller. And look, we have these traces going to it and some wires. These traces have parasitic resistances, but most of all parasitic inductance. That generates voltage spikes, interference, and maybe in some conditions the snubber didn't do its job. The MOSFET received a way too high voltage, it broke down, and the controller exploded. Why did they put the transformer so far over here? I'm not sure. Maybe they wanted to make sure that the board looks well, but my idea is that first of all the board should work well. Also, it should have had some fuse in series with the controller. When the MOSFET inside the controller shorted, if it had some fuse, the controller wouldn't have exploded because the fuse would have blown. I traced out these diodes. They are not for feedback purposes. No, as far as I can see, each one of them is a separate power supply for the controller side of the modules. Each diode supply power to one of these connectors. Why did they need to have each module separate power for the controller part? I'm not sure, maybe for isolation purposes, but this is what they do. But this isn't that great either, because you are sending high frequency square wave pulses on such a thin traces and very close together. You are asking for trouble, you are asking for interference. Also, these connectors for the 319 volts, 90 volts for the modules. The spacing between the pins is too small. Granted, the center pins don't seem to be connected anywhere, but still, you could get arcing. Someone said in the comment section of Tony's video that flyback controller failing is a common thing with these power supplies. So yeah, maybe the power transformer here wasn't that great idea, but enough me complaining about things I cannot control. Now, someone said in the comment section on Tony's video that the connection between this capacitor's ground and the main capacitor ground should be checked. It is a connection inside the board and sometimes it fails, so it needs to be checked out. There you go. It is there. Another thing that was pointed out is this Zener diode, a 5.1 volts Zener diode. Sometimes it shorts out. So, not shorted. Yep, the Zener is okay. And one more thing that was pointed out in the video, in the comments section, was that the PFC section would start only when there is some load on the outputs. So I need to check that. But I cannot do that just yet because I already found an issue, something that Tony missed. I would have missed it also if I hadn't reverse engineered the board. What did I found? Well, even if you see something here? No, you can't. I didn't even see it. But when I reverse engineered the board, I felt I needed to check the continuity. I knew that this should have continuity with this. I knew there was a trace, but I didn't see it was interrupted. Still, I needed to check, and it is interrupted. Luckily, I do have my new microscope, and what do you know? Let me get closer. A melted track. Now, why would that track melt? The track that melted is this part here. It comes from pin number 4 of the controller IC. This pin reads the rectified mains voltage, and through some RC filtering, it converts it into a proportional current reference. And since it melted away, the controller couldn't work. I'm not sure, I haven't tested it because I wanted to do that on video, but I think this should be the only problem with the PFC. This is pin number 4 of the controller. And this is where that track comes, after those 3 resistors. Of course the controller couldn't work, because it couldn't generate a current waveform reference for the current amplifier. Why did this track melted? It can't be from high current, because this is a 250k resistor, and there are other two in series with it, this one and this one. So the impedance is huge. Doesn't matter what the controller does. So remember this melted track? It got pulverized. Well, either this track jumped somehow here and melted the track, or when the controller exploded, some melted metal jumped in here. Because remember, the board was covered like this. And look. When the controller exploded, it met this, and the explosion was spread out on the board. This is what I think it happened. So, what comes next? Well, I need to fix this part. And also, maybe you have noticed, when I reverse engineered the board, I needed to desolder this capacitor and the comparator. I wasn't sure about some of the traces and I needed to make sure. I'll solder them back on, repair the trace, and test the supply. I am using 0.25 millimeters leaded solder wire. The thinner the solder wire it is, the better job you do with soldering, and also the lower the waste. Do we have continuity now? Of course we do. And here also. Yep. I am ready to test. I have my multimeter connected across the main filtering capacitors on the PFC's output. I have my improvised current limiter, a 200 watts light bulb. I wanted a bigger one just to give enough juice to the power supply and yet have some form of protection in case it goes boom. I have here main socket, live, neutral, and earth. And let's test it, shall we? When I insert this here, either it goes boom or we'll read 390 volts on the multimeter. So 3, 2, 1, go. No PFC. Still no PFC. Look at the multimeter. It seems to want to go high. Does it really need a load on the output? I'm not sure. For a moment there, it seemed to want to go to where it should be. I want to make sure that the PFC controller does get its power on pin number 19, so I connected the multimeter there, and let's see. It should have 12 volts or thereabouts. 13.3. Yeah, it does. First of all, please do not do this at home if you are not 100% sure of what you are doing. Anywhere on this board, there could be lethal voltages. So yeah, if you're not sure, don't do it. Now, I have connected a 100 watts light bulb, another bulb, a smaller one, across the main filter capacitors, just to give it some load. I know the light bulb draws a lot of current at cold, but still, a 100 watts light bulb shouldn't be a problem for 1000 watts PFC. So let's see. 3, 2, 1, go. The line voltage dropped too much on this light bulb. I have connected another 100 watts light bulb in series with that one to decrease the load on the output. I do have some resistive loads, but they are a high power ones, and I wanted to test at light loads. And light bulbs, I think, are still the easiest way to do it. So let's see now. Still too much voltage drop on the mains light bulb. I have replaced the light bulb on the mains with a sacrificial fuse. I must say it again, do not do this at home if you are not 100% sure of yourself. It's not worth dying over. Three, two, one, go. No, still no PFC. The light bulbs should have drawn enough power from the PFC to make it work, but it didn't. Why is that? So maybe, as I suspected, the PFC doesn't really need a load on the output. I was preparing to test some voltages on the pins of the PFC controllers, so I have soldered some wires here to connect my multimeters to them because I don't want to get near the deadly voltages on this side. And through redundancy, which sometimes pays out, I found a problem. I wanted to make sure, remember this melted trace which we fixed? Well, I wanted to make sure that pin number 4, which is this one, does have a connection through here. What, a mega ohm or something, right? No, less than that. 750 Ks or something like that. Watch what happens when I put my multimeters here on pin number 4 and here on the melted trace, on the fixed trace. 20 mega ohms. How on earth could that be? Well, I traced it starting from pin number 4, which goes in here, then through this resistor here, 247 kilo ohms, then another resistor, which makes 495 kilo ohms, then here at this resistor, again 495, so it's okay, then here. Well, it is not okay anymore. And look, when I connect my multimeter across the resistor, so that resistor failed. Why on earth would such a large resistor fail? I have lowered my microscope to see it up close. Is it cracked? Doesn't seem to be, right? Or is it? Is this a crack? Microscopic one? I don't think so. So what happened? What on earth happened? Is this pad disconnected? Really? Did I damage it when I fixed the trace? Let's see. If I put the multimeter here. Yep. 248 kilo ohms. Yep. I damaged it. Now it should be okay, right? Let's see. Come on. Yes, 247 kilo ohms. And if I put my multimeter on pin number 4, do I get my 700 kilo ohms? Yep, I do. Soldering now looks good, right? Well, let's see. I am now ready to test again. Do we or do we not have a working PFC? Let's see. 3, 2, 1, go. Yeah! Victory! Damn! Those light bulbs really light up. 395 volts. So it works. It was my bad, sorry. I have damaged the poor resistor. What if I disconnect the load from the output? Will the PFC still work? Let's see. In 3, 2, 1, go. Yes, it does. 397. So it works. What comes next? Well, desoldering these wires, of course. Then replacing the fuses. Replacing the fuses with those that Tony sent me for the supply. And then putting it back in its case. So as I said, reverse engineering sometimes pays up because it helped me understand the circuit. It helped me understand the pin functions and traces and components, layout, and so on. And of course, redundancy. Never make assumptions. Always measure. Never make an assumption that this trace is good, so I will not test it. No, you always test it. You always suspect something is bad. You always suspect a trace is bad, so I need to measure it. You always suspect a component is bad, so let's measure it. That's why we have testing gear. And of course, a microscope helps. I think without it, it would have been a nightmare reverse engineering this board. Yeah, let's put the fuses back. Leads are too short. This heat shrink has a heat activated glue coating on the inside, so it does a better job at staying in place. There we go, problem fixed. This is my solder wire, 1mm leaded solder. I used it for through-hole components. I need to stress again the fact that you should never work on mains powered boards if you are not 100% sure of what you are doing. It is not worth the risk, trust me. Now, before I put it back into its case, I wanted to test one last time to make sure we still have a working PFC. So, without further ado, 3, 2, 1, go. 396. Yep. The power supply is back in its case. All the screws are there. But before I get done with the video, I want to test that global inhibit function to make sure I have outputs and a working fan. So, as you remember from Tony's video, on this connector, pin 1 must be connected to pin 8, this green jumper wire, and pin 2 must be connected to pin 7 with a resistor. It should be 800 ohms. I am using a 910 ohms. Should be just the same. And I'm connecting the power now. Okay, the fan started. The resistor wasn't pushed all the way in. So we have a working fan. How about 12 volts? Sorry, my multimeter lost its connections momentarily with the laptop. So again, 12 volts. It's the other way around. 11.98. Close enough. 24. 24,001. Wow. Tightly regulated. The fan is spinning. So this is it. And this, if I remove this resistor, the fan should stop, right? Yep. What if I put it back again? Yep, it started. Yeah. So this is it. As I like to say in my videos, in my Romanian language, of course, yay, victory! We did it. we fixed it. And I'm happy I did. Quite beefy power supply, but let's say it has some vulnerabilities. I have pointed out them in the video. Before closing, I know my English sounds horrible, and I do apologize for that. Trust me, it isn't ignorance. I do read, write, and understand a very good English, but when it comes to speaking, I get quite nervous, and the lack of practice makes me sound horrible. I know. I am sorry. I am trying to do better, and this only comes with practice. So many more videos like this. I'm hoping I do not annoy you too much. So this is it. This is the video. The other power supply will be dealt with in the next video. So if you watched until the end, thank you. Thank you very much. If you liked it, please give it a thumbs up. Please subscribe. It helps with my channel. If you like my work, you can support me by buying super thanks or becoming a member of the channel. So without further ado, thank you all. Thank you, Tony, for trusting me with this. And we'll see each other in the next video. Bye.